Last time we have seen a concept of operators and what are the importance of these operators in quantum mechanics. Today we are going to see one more concept, and that is a commutator. So in examination you will get a simple question, what is a commutator, and some examples derive the relation between position and momentum operator in commutator relations. Okay, first we see what is this concept, and for that measurement in a classically first we see, and how that we'll see in terms of a quantum mechanics. Okay, so in classical mechanics, say position, this position is denoted or measured in terms of x, say x position, and if we see in the quantum mechanically, position is one, another is momentum, a p is equal to mass into its velocity, momentum, then energy E is equal to the total energy. If you see it is the total energy, then total energy is equal to kinetic energy plus potential energy, and therefore this is a Ke plus a potential energy. So these are the classically. If we see in terms of a quantum, if we see in terms of a quantum mechanical view, then how that a position, momentum and energy, and these are the in quantum mechanics works as an operator. So this is the operator X. So that cap is we do not for the operator. Momentum, the momentum operator P cap. Okay, this momentum operator is equal to, we know that I h cross del, and we know that this del is a Laplacian operator, so that is the delta by delta x plus delta by delta y plus delta by delta z. That means this P has a three component: the momentum along the momentum operator along the x-axis, y-axis and z-axis, and therefore this px is equal to minus I h cross delta by delta x, py is equal to minus I h cross delta by delta y, and pz is equal to minus I h cross delta by delta z. Okay, so this is the momentum operator in terms of quantum mechanics. The energy, and this energy operator, the energy operator is equal to this I h cross delta by delta t, delta by delta t. Okay, so this is the basic difference between the measurement in a classical and in quantum mechanics. When we talk about in quantum mechanics, that is this measurement are in terms of the operators. Okay, and this operator is related to the its a process of the measurement. Say x operator is the position operator, is related to the measurement of a position. This momentum operator is a process or operation to the momentum operator, and like this. So this is the a basic difference between a classically and quantum mechanically. The operator A, and there is another operator P, which are associated with a dynamical variable A and P. So this A is related to the dynamical variable of A, and B is related to the dynamical variable P, and its commutator is defined as A bracket AB. You write this as and read as a commutator AB is equal to into simple bracket AB minus BA. So the commutator of AB is defined as a simple bracket AB minus BA, or this can be written in terms of the first and second. So 1 and 2. So first and second. So first into second minus second into first. Okay, so this is the mathematical definition of a commutator. Now we will take a simple example of a position and momentum. So position, say along the x-axis, x is a position operator, and a px is its momentum operator and commutator of this. Now when we talk about this commutator, then we have to find out what is this value. But if you see this a p of x is equal to minus I h cross deva by deva x, which is minus I h cross deva by deva x. Here it has nothing to represent, only this px, unless and until it acts on something. It acts on the wave function, it acts on the in state of quantum mechanics, and therefore only the operator px has no physical significance, and therefore it acts on something, and therefore we acts on a sign is equal to. So commutator acts on a state sign. Then what we are going to see, so that is the x into the commutator of x, and px is a, so that is a minus I h cross deva by deva x sign is equal to simple bracket, so that minus I h cross will take common as, so this is the x deva by deva x minus deva by deva x of x, bracket completed, the sign is equal to minus I h cross x, now coming inside, so this dou psi by dou x minus deva by deva x of x sign, whole bracket completed. So there are the differentiation of the first and second, that rule. So that is the minus I h cross x deva psi by deva x minus first x into deva psi by deva x minus deva x by deva x into a sine, bracket completed. Okay, now these two terms are the same, and one is the plus, another is the minus, therefore cancel to each other. Okay, now is equal to minus I h cross minus into bracket deva x by deva x into sine. So this is the differentiation of x with respect to x, and that is the value is equal to 1, and is equal to minus I h cross minus sine is equal to I h cross sine is equal to what? Is equal to, so that is the operator of x, a px of sine. So a commutator operates on sine is equal to I h cross sine, and therefore value of this commutator x px is equal to I h cross h px is equal to I h cross. So this is the value of this commutator. Okay, means x is the measurement of a position along the x-axis, and px is the measurement of a momentum along the x-axis. Okay, therefore, and that this value is equal to I h cross. Now we are going to see another relation. If x is the measuring into the x-axis, x is a measurement in x-axis, and we are going to see what will the momentum along the y-axis. So that is the py, and see what happens. Now, so this is the x and a py. Okay, is equal to what happens for this x on sine, then x minus IH cross 2 by 2y psi is equal to into simple bracket or minus IH cross into bracket x double y minus double y of x bracket completed psi is equal to minus IH cross x double x minus, so this double y of double y and x psi. So x is a constant and psi is termed as a function, and therefore IH cross x double y minus x double y, and these are 0. These are 0, and therefore the total value is equal to 0. 0 into psi is equal to 0, and therefore the value of x and py is equal to 0. Means whenever we are talking about the measurement along the one axis and its momentum along the another axis, then its commutator is equal to 0. Okay, so alternatively, so this x into x and px is equal to IH cross. This is the alternative way to represent uncertainty principle. What is that uncertainty principle? So that is the delta x into delta px is greater than or equal to h cross by 2. Okay, so this is the alternative representation of your Heisenberg uncertainty principle. Now, this what is the meaning of this x px is equal to IH cross and x py is equal to 0? Okay, means this when we are measuring the position accurately along the x-axis, then we cannot make simultaneous measurement of px. Okay, and therefore it is equal to IH cross. And when we are measuring this x and py is equal to 0, it shows that x is we can measure precisely as we want, and the py is a momentum along the y we can measure precisely and accurately. That means there is no effect of this process of the measurement on the measurement of a py. So momentum along the y-axis, whereas the position along the x-axis, and therefore they are the non-effect. There is no effect on each other, and therefore its momentum is equal to 0. In another way, if A and B is any operators and they have no communication, they have no effect on each other, then so there are no relation between any two, then we can say that its momentum, its commutator is equal to 0. Its commutator is equal to 0. Okay, so this is the relation between a commutator. Simultaneously, the other relation we can write. So this x along a p side, a commutator is equal to 0. Then y and px, a commutator is equal to 0. Then y p side is equal to 0. And z px is equal to 0, z and py is equal to 0. Okay, and IH cross, so this is the x and px is equal to y, so these are commutators, y p1 is equal to z and pz is equal to IH cross. Is equal to IH cross. Okay, so this can be represented in chronicle delta, but don't confuse for that. We'll see later. So these are the concept of the commutator. Now we'll see what are the basic properties of that commutator. Let A and B are the operators corresponding to a dynamical variable A and B, and therefore this commutation relation AB operator, AB commutator is equal to AB minus BA. Then if this commutation is equal to commutator is equal to 0, then these two operators A and B are said to be a commute. If it is not equal to 0, then it is not a committed, not commit to each other. If this a commutator is equal to 0, that means this A and B are independent to each other. The properties of the A, operator A, and the properties of the B are not influencing to each other, and therefore this commutator is equal to 0. So this relation shows that, and then we say these two operators A and B are said to be commute. Okay. Now there are some algebraic properties of a commutator that we have seen in mathematics also. So that a commutator of the AB is equal to minus of BA. If you reverse that, then a sign will change. Then there are the three operators. So A, B, and C. Then commutator of the A, B, C is equal to the commutator of the first two into third one plus second one into commutator of the AC, and therefore this can be read as that the commutator of the ABC is equal to commutator of AB into C plus B into commutator of AC. So this can be written in terms of the 1, 2, 3 like that. Then commutator of A and sum of the B and C is equal to this sum is a common to each. Then commutator of this AB plus commutator of the AC. So this A is a common to B and C. Okay. Then a product rule. This AB, the product of the AB and C, commutator of C. Then this AC, a commutator of the AC into B plus A into commutator of the BC. Okay, and the fifth one, so there are the commutator inside also one commutator of the commutator. So this A commutator of B and C, then this B into commutator of AC plus a C into commutator of AB is equal to 0. So this is the main. And if any scalar quantity is multiplied, can be multiplied this one, and therefore this x is a scalar. Here y is the scalar. If x is the multiply to the A, then commutator of this x A commutator of B is equal to x into commutator of AB. If y is the any scalar and then multiply to the B operator, then operator A commutator of operator A y B is equal to y into commutator of AB. So these are the algebraic properties of a commutator. Let us consider A and B are two operators corresponding to a dynamical parameter A and B, and therefore it's when A operates on psi is the any wave function or any state of quantum mechanical particle, so that A operates on psi is equal to A psi, where A is eigenvalue. Then this B operates on psi is equal to a B psi, where the psi is a eigenfunction and AB are corresponding eigenvalues. Okay, then this psi is called a simultaneous eigenfunction. Why it is called simultaneous? Because when A operates on psi, we get the A psi. Eigenvalue is A and eigenfunction is psi. And B operates on psi is equal to a B psi. Eigenvalue will change, but the eigenfunction will be the same. And therefore, this psi are the same one. And therefore, it is called a simultaneous eigenfunction. Now, see, there is another property we can say. When this AB operates on psi, then first A operates on psi. A operates on psi, therefore we will get the A psi and B outside. Now this A is scalar. It is eigenvalue. It will come out and A into B psi when B operates on psi is equal to this AB psi. Okay. Now reverse the operation here. So this AB psi means first B will act on psi and afterward A. Therefore the operator A into bracket B psi, B is the scalar taken outside. So this is B into bracket A operates on psi, and when A operates on psi, so that is the A psi, and therefore it is the BA psi. Take the difference of these two, then for AB minus BA psi is equal to BA minus AB is equal to psi. So differentiation of this. But this AB and BA are a scalar one. Therefore, this AB is equal to BA, and therefore this bracket is equal to 0, and therefore this AB minus BA is acts as operator. So this is the new operator. By combination of this operator AB, so this AB minus BA is a third operator, operates on psi is equal to 0 with eigenvalue 0, and therefore psi is eigenfunction for AB as well as for the AB minus BA.